Good morning to all the participants. Good morning, Professor Mao, and I warmly welcome to all of you on the 7th day of Indo-US Webinar and Lecture Series. So today we have two lectures. First lecture will be delivered by Professor Mao, and it will be from 10 to 11:30. And the second lecture will be from Professor Banerjee from 11:45 to 1:15. So, Professor Mao, if you need some break between your lecture, you are free to announce for the break anytime for a short break if you want. So with these words, I request Professor Mao to start his special lecture, Designing Phosphors for Solid State Lighting. Thank you, Professor Mao.
Thank you, Dr. Ahmad. So let's start. We'll see. Maybe let's get it done. All in once. Then if we have more questions, we can discuss the questions, and then maybe we can finish in a few minutes earlier if that's okay. Yeah, so I'm going to talk about how do we design in phosphors for solid state lighting, and the solid state lighting is really a hot topic now, other than people working with energy storage, for example, lithium-ion batteries, those type of energy conversion. I mean, this is also a type of energy conversion process as well. To do that, today actually I'm going to spend some time to talking about the solid state lighting, especially light emitting diodes. And once we, and how do we characterize LEDs? Once we have that, I will show you one example of a phosphorus, which my research group have been working on. Because there are lots of phosphors, being designed in the literature, and I just don't want to repeat that, but once we get to the fundamentals, then it will be much easier to understand, why we design phosphors and how to design phosphors. So that's the plan. Okay. So first, I want to show you, right? Basically, when we talk about the phosphors, basically it's the light and the matter interaction. Right. So here I'm showing you two photos. Okay. And actually, first I want to ask you what's the difference looking at this when we look at these two photos. Okay, just give you a few seconds. One thing you may notice. Okay, they are both colorful, right? They're wonderful, and we like colors, different colors. But then in terms of a difference, right? The first one, the background is white. The second one, the background is black, right? So in general, that gives us a hint and what's the difference. So the first one is actually this shows the pigments. That's how when we do the paintings, what do we use? And the second one is related to the phosphorus, what we are going to talk about today, right? So basically phosphorus, it happens is when we excite the materials and then, they were luminescent. That's the difference. And of course, in terms of the physical support, right? The pigments, they react differently, right? So the light hit on this pigment, and then part of the light will be absorbed by the pigments, and then part of it will be reflected, right? And then that's what we see, the colors of the pigment, right? But the phosphorus is the process is completely different, right? So they are electronic transitions, right, from different energy levels. Okay, we'll go back to this, different energy levels just in a little bit, but that's the difference. Okay, so with that, right, then we need to get back into the, to the fundamentals. What is luminescence, right? So luminescence is actually, by definition, is a light emission which represent an excess over the thermal radiation. Okay, so luminescence is not a thermal radiation, right? And then also it will last a time exceeding the period of electromagnetic oscillation. So so when the excitation, stopped, right, the luminescence could still exist. Depends on the time scale. We will talk about that, a little bit today and especially tomorrow, and we will see that. And then is a form of cold body radiation. So the luminescence is different from the incandescent light, right? Incandescent light is a thermal process, right? The thermal radiation. So that's the difference as well. We'll talk about the incandescent light today as well. Then losses the correlation between phases of absorbed and emitted light. Okay, so that's also difference in terms of the luminescence. So there are so many types of luminescence, depends on the excitation source mostly. So the most common ones we're talking about is the photoluminescence. And then, if it's electrically excited, then it gives the electroluminescence. That's actually the LED is how it works. And then, it also gives the tripoluminescence, crystal luminescence, solar luminescence. And then the other type of luminescence, which, it happens in nature, is chemiluminescence. That part, it also has if it's related to bio, it's called bioluminescence. Then the radioluminescence, which is widely used for scintillations. So we will talk about this tomorrow, and then luminescence as well. Then the other thing is, in literature, and we probably hear a lot about the fluorescence and phosphorescence. The difference between these two is, the fluorescence is faster, and then phosphorescence is a slower process. And but nowadays, we just in general we call both of them as luminescence or just photoluminescence, right? Then there's another one is called the mechanoluminescence. So what this is, for some type of phosphorus, right? When we apply some pressure on it, and it will luminescent. And this is actually a very good material for sensors. And there are some studies, actually quite some studies on this mechanoluminescence nowadays as well. So so that's in general, how different the type of luminescence we are talking about here, right? So I will give you some samples, related to some of this, and mostly tomorrow. But today I will just start with this. So then in terms of luminescence, something we familiar with, it's called the Stokes shift, right? So the general luminescence is actually, it has a Stokes shift. So basically, the phosphorus absorbs the material, absorbs the light, right? And then it will emit light at a different wavelength. And that wavelength is actually at a long wavelength. That's a Stokes shift. But there are the other type of luminescence as well, some phosphorus can absorb the light at a longer wavelength and then emit the light at a shorter wavelength. And that is called the anti-Stokes shift. Okay. So again, tomorrow we will talk about this, but I want to give you this background information today. And also I want to talk a little bit about the history of luminescence. Afterglow, and nowadays we actually, there are sometimes we hear about these terms. So afterglow is actually, it can trace back to about 1,000 years. In the Chinese history, actually they were recording about this afterglow, which about 1,000 years ago. And then after a long time, then They first actually observed fluorescence from quinine by Sir Herschel in 1845. And so that is more from a type of organic compound, right? And then in 1853, Stokes coined the term fluorescence. And also that's related to, right, Stokes shift and the Stokes shift, right? That's what we have here. And then in 1888, Wiedemann used the term luminescence, okay? So you see, right, then slowly, right, in the 1920s and the 1930s, and then the basic principles of fluorescence was mostly developed. And then by that time, so about 100 years ago, slowly luminescence started to become a science, right? So then, during that in 1920s and the 1930s, there is Galvin law, developed the excited state lifetime idea, and then Valiloff started use the quantum yield, and then later on there is a polarization of fluorescence as well, and then the other one is called very important diagram is Jablonski diagram, and we will show that as well. And then, in the 1950s, right, the fluorescence resonance energy transfer actually explored by Foster. And that, for those of you who work with bioimaging, that's actually very common thing, but now that it's actually developed in the 1950s. And then in the 1960s, Arzel actually developed the up conversion. Up conversion is exactly actually related to this anti-Stokes shift. So again, I will show you some examples tomorrow. So that hopefully that gives you a little bit, history, brief history about luminescence. And some of this is actually I want to show you, right? Jablonski diagram is actually, this is very important to explain fluorescence and phosphorescence process. Right, so the plot on this side shows the absorption of materials, right? When we excite the materials, then the material will absorb some energy, and then if we take the absorption spectrum, then it will be something like this, right? Basically, this is only about the absorption of the light, right? So once the material absorbs the light, right, then there will be many processes happen, in the materials, right? One of this is related to fluorescence, right? Of course, there will be other processes as well. For example, it's okay, because of the getting back. So after the absorption, right, the materials inside the material, then there will be vibrational relaxation and also internal conversion, right? So once that happens, then especially you see the absorbed energy goes up there, and then some of the relaxation. Once some of the relaxation happens, then the material will start luminescent, and then that gives the fluorescence. But if there is a transition, if there is an intersystem crossing. For example, from this S1 to this T1, and then that will take some time, and then eventually they give the luminescence as well. And then because of that extra time, and this process is called phosphorescence. And one important thing is here, right? The time scale. So you can see the absorption, process by materials is pretty fast. Okay, is a femtosecond, and then the vibrational relaxation and the internal conversion normally is about a picosecond, right? The fluorescence is about a nanosecond, but the phosphorescence is microsecond. So that's the general idea about this fluorescence and phosphorescence. And then so then the important thing is, right, we study phosphorus, right? How do we characterize them? How do we take the spectrum you know, for example, phosphorescence and fluorescence spectrum, right? So I'm going to talk a little bit about this excitation and the emission spectrum, right? So when we have our samples, okay, we place our samples here, right? And then this side is the excitation source, and then this spot is the detectors, right? So we can detect the emission from our samples. And to take to get the excitation spectrum, and then the emission monochromator is fixed. Okay, so we take the emission at a specific wavelength, emission wavelength, and then this is the detector. And then we got the I emission, right? But then the important thing is on the to get the excitation spectrum, the most important thing is on the excitation side. So the excitation monochromator is actually moving. So it was basically scanned at a different wavelengths. So that gives us the excitation spectrum. And then, of course, right, the light source is very important. In general, for luminescence measurements, you know, we use a xenon lamp or arc lamps. You know, especially when we talk about the phosphorus for lighting, and that's a common one. But of course, if we want to go to UV light, or if we want to get the infrared, you know, then the light source could be different. So we also can use specific lasers as a light source, and so that's the other thing. And tomorrow when I talk about the up conversion, you know, those type of processes, we normally use a laser. So that's the other thing, you know, you will realize. And so that is about the excitation spectrum. Then in terms of the emission spectrum, then is the opposite. So here, you know, the excitation source actually wavelength is fixed, and then on the emission monochromator is moving. So we can get you know, the emission spectrum, and then again samples are located here, right? So that gives us a little bit idea. And also then the other thing, important thing is we need to understand, you know, what's the difference between here, if I go back here, right, you know, what's the difference between the absorption and the excitation spectrum, right? So absorption is also, you know, related to the excitation source, right? And it is just the material at which wavelengths, right, it will absorb the excitation light. Then the excitation spectrum is looks, you know, it also looks similar, right? So that's why I want to show you this. So you will see that, you know, this is most of the time actually the absorption and the absorption spectrum and the excitation spectrum, you know, their peak position are quite, you know, are similar. But because of the excitation and the absorption process, you know, is the measurements actually are different. And so that's why you see the intensity of those peaks are different between the absorption spectrum and the excitation spectrum. But then for the emission spectrum, as we talked earlier, you know, there is a Stokes shift. So that's why we see these peaks are at different locations, right? But it's close to, you know, if there is an excitation spectrum, normally excitation peak, then we could expect there is emission peak. And so that's, you know, that gives us a little bit idea about this. You see here as well. So, and then the next thing is you know, luminescence quantum yield. Quantum yield, right? You know, for a lot of us, when we hear about quantum, and then normally, you know, yeah, that means it's complicated, right? But you know, we'll see what it is. Okay, quantum yield is you know, it's not. It's a very important parameter, but it's not too difficult to take the measurements. So, so here, you know, again, we use a light source, right? And then goes through the lens, and then the most important part is we will have an integrating sphere. and then we mount the sample most of the time in the center of the sphere, right? And then you know the light hit on the sample, and then it will luminescent. It will, and then because of this integrating sphere, and it will be all reflected, and eventually, you know, at this part we have a diffuser, and then we can take the signal here, immediate light here, and then again we use a spectrometer, and then we get the data, right? So in this process, there are a few things we need to understand, right? So so here we measure the immediate photons, right? This part, you know, you detect, you know, it's related to the absorbed photons, right? So the quantum yield basically is the number of immediate photons divided by the number of absorbed photons, right? So how do we get the number of immediate photons? And so the one thing is, to get that, we always need to do two measurements. One is, you know, there is no sample in this sample holder. Okay, that's one measurement. So and then we also need to, then we put the sample in, and then we take another measurement. So that will give us the number of immediate photons, the number of absorbed photons. So maybe it's better to look at this this figure is better. So when there is no sample on the sample holder, and then this is basically the absorbed photons, right? So and then, you know, because there is no luminescence, no phosphorus there, right? So there is no luminescence. So that gives us the so we don't see emission here, right? And then when we put the sample in, because of the phosphorus will absorb a certain number of photons, right? So the peak here is lower, but at the same time, because it absorbs the photons, and then it will give immediate photons as well. So if we put these values and in this equation, and then it will be equal to PB minus PA. So PB is this one, right? And the PA is here, okay? And then we'll, for the absorbed number of absorbed photons, it will be equal to LA minus LP. So that is how we get the quantum yield. So that's the other thing, and also because of the luminescence is actually quite a dynamic process. So we can we also normally, to evaluate phosphorus, the phosphor, we also started the luminescence lifetime. And so before that, you know, we need to look into this, right? So it's actually the luminescence process is actually quite a complicated process. Okay, there are many photons, and also there are many escape pathways, right? For example, okay, so this is schematically showing that okay, so this is the excitation, okay, and the heat on our samples, and then you will see that, you know, there will be energy transfer to acceptors. Okay, I will talk a little bit about this, right? You know, what is acceptors, what is a host. So, and then, you know, either it will get luminescence out, right? Or it will go through the intersystem crossing, as I mentioned to you earlier, right? And then there will be internal conversion as well, for example, to heat, right? This is related to the efficiency of phosphorus, okay, this heat. And of course, we should all minimize this, but, you know, there's always, you know, because this is a wavelength conversion process, right? So there's always heat generated. And then there could be a quenching processes as well, okay? You know, hopefully there is no destructive chemical reactions, you know, or for the bleaching, but some materials do, especially organic phosphorus, right? But today, you know, my background is more for talking about inorganic phosphorus. So normally we don't experience this, but that could happen, right? So, you know, all this takes some time, right, to process. So you know, in general, then the lifetime of the excited state will be equal to all these terms together, right? All these processes together, right? So that's what we, you know, we want to try to understand the materials, right? Of course, you know, depends on the you know, this decay time, right? It has, you know, in certain time, you know, range. So you know, a lot of times, you know, it may not be this complicated. Depends on the time scale we are looking at. So but there's an important thing is, you know, so we excited, then the light will, you know, decay, and then we will be able to get the decay time. And when it is reach this, you know, E, 1 over E in terms of the intensity. So, you know, if we really want to look into this more details, right, you know, of course, this excitation, you know, we give a pulse of excitation to our samples, then we stop it, right? And then we will be able to, connect the light and see how fast they decay like this. So that's the schematic. This part basically is also the excitation source, and then the driver, basically the driver unit, and then, you know, it go to the samples, and then eventually go to the readout device. So that's basically, you know, what happens. But of course, right, you know, it's not always like this exponential decay, right? Depends on, you know, how this type of different processes involved. Sometimes there may be multiple processes involved, and they have different time scales, decay time scales, and then we could get a decay plot like this. Okay, so definitely you will see that there's two, you know, the slopes are different, right? For this part, the slope is here, and then for this part, the slope is here, and even there is a tail here as well, right? So when we analyze our data, and then, you know, we divide them into different into the different time scales. And then, you know, in this way, it will give us tau 1, and then for this part, it will give us tau 2. And then we can correspond this to different decay processes. Okay, so when we talk about, you know, when we characterize luminescent materials, these are the common processes. Yeah, so, you know, then, right, so we know how to characterize the luminescence. Those three are three common techniques. Okay, then, you know, in terms of luminescence, the materials, a lot of times actually, you know, we have excitation, and then, you know, it will be absorbed, right, and they give emission, and then also photons that give us the heat, right? So, and then this is the A actually represents the activators. So a lot of times that is the dopants, and we intentionally add those dopants into our host materials. And so yeah, so these time scales are, you know, are different, right? For example, here I'm trying to show you this, right? Depends on the excitation source. A lot of times, you know, we say the pumping, right? It's really like a pump, you know. We pump the electrons to the higher energy levels, right? And then, you know, these energy levels, you know, they sometimes, you know, the excited electrons could go through some of the non-radiative processes, right? You know, they could go through some transition processes as well, right? And then, you know, they stay at this metastable level, and then eventually they give light out. And depends on what these metastable levels, you know, and this is actually for the laser, how laser processes happens as well, you know, and then, you know, at a certain time they give the laser out. So yeah, this is just in another way to show this, you know, a simpler way to show this process, right? You know, basically excited, right, and then go through the non-radiation process, and then at this energy level, then it will emit light. And so a lot of that, how we correlated to this, right, in the atomic distance. So this basically is related to the ground state, right? Ground state here, right? Here, schematically, this is the ground state. Also here, this G represents the ground state. And then, to show the excited state, and that is the excited state, right? If there is a phosphorescence process, then the excited electrons will transfer to the triplet level, right? So that's why from here you see the fluorescence, and then this is the photofluorescence, right? So this is the distance between these two lines. Between this is related to the Stokes shift, right? So if we want to avoid too many photons generated, then we hope these two levels, this should be closer as possible. So that's yeah. So I'm showing here, that's a Stokes shift, right? Absorption and then emission, the emission, and that gives that. And yeah, so I think then how this excitation emission related to the host materials, right? So here is actually this process is related to the activators, right? But remember, right, the activators is actually for a phosphor. It has two parts, right? It's the activator and also there is a host material. So how this related to because the host material, right? It has a valence band, it has a band structure, right? So how this, how these two components are connected. So here showing, schematically like this. So this valence band and the conduction band is actually comes from the host materials. And then we will have some of these energy levels, for example, here I'm showing the manganese 2+, the example, right? So these are the energy levels of the manganese 2+, right? It would be sitting in this band, or, it will maybe saddled on the conduction band or the valence band, right? But really, if we want to get the emission from these dopants, right, this energy levels should be within the band structure of the host materials. Okay, so that is the other thing, how do we get connected with this, right? Our objectives, right, we're talking a lot about this, is, we want to search new host materials. And as I mentioned just in a little bit, we want to develop nanoscopic light emitters. Then, the other important thing is how can we enhance luminescence? That's always something, right? So we explore strategies to enhance luminescence. That's something we'll talk more tomorrow. And right, for science projects, right, we always understand the structure related to mechanism, right? Why some host materials and combined with the activators works, give very good quantum yield, right, but not the others. So that's the, in general, how we study the phosphorus, right? And then in terms of the luminescence, the phosphorus, right, the dopants, most of the time we use these real earth dopants, right? But also we can use some of these transition elements. And one of these things is about the phosphorus luminescent materials. They emit light can be, in a quite wide range. So we can tune, basically, we can tune the colors, what the colors emit, right? So for example, here actually showing some of these transitions for these real earth elements, right? You can see, from UV to visible light to infrared, okay? And this is actually just part of it, right? It can go to mid-infrared as well, so that gives a lot of, potentials about this luminescence. So So, once we have the understanding on this, and then it will be much easier for us to understand the solid state lighting. Okay, and then, my topic today, I'm trying to talk about the nanomaterials, right? So what's the unique part about the nanomaterials? So in general and potentially, okay, so, we could get high quantum efficiencies and sharp emission peaks, high photo stability and emission wavelength tunability, and may emit light when irradiated by even ionizing radiation. So, for nanomaterials, that could be potentially. And even though this is not our focus today and tomorrow, today, for bioimaging, there are different materials being explored, and also for bioimaging is very important, right? We use nanomaterials or we use molecules, right? So in terms of organic dyes, that has been used, explored, but they suffer from photobleaching and broad emission, right? That's one thing I mentioned to you earlier, right? Photobleaching is a problem for organic dyes, and then because of the organic compounds, right? Their structure is more, they can vibrate more easily, so they give broad emissions. And then, there are also people try to explore quantum dots for this purpose. But then that, right? Many quantum dots actually are quite toxic. So that's why we, for the luminescent nanomaterials we've been working on, and we use lanthanide doped nanoparticles, and then this really have many advantages. For example, the wide excitation range, as I showed you earlier, it covers UV to near infrared, and broad emission wavelengths, and enhanced photo stability. It doesn't have the photobleaching problem, large Stokes shift, and the increased lifetime. It can reach milliseconds. So then, as I'm going to talk tomorrow, we can get up conversion as well. And then high water dispersibility, and that gives the biocompatibility as well. So this is just a few aspects, in terms of the bioimaging, right? So analysis, optical imaging, cell labeling, drug delivery, and tumor therapy. And all this, have been explored with this lanthanide doped nanoparticles. So, if you are interested with luminescent nanomaterials or any of this, could be very interesting. So, so there's a lot of things we can do. Just you need the teamwork as well. So, of course, today, my topic is about solid state lighting. So I will switch gear for now. Okay, I hope so far I gave you a brief background about the luminescence and luminescent materials. And so from luminescence to lighting, right? This is really a key, right? Because we want to have light, and we want to have light which is close to nature light, right? Sunlight. So, and also we want to make it as efficient as possible, right? So this slide, really gave us that, we see how, this developed in the, in our human history, right? And the first one, of course, right, 1,000 years ago, right, people started using oil lamps, right? And but those oil lamps gave very little amount of light, right? And then slowly in the 19th centuries, finally, humankind developed light bulbs, right? So it gave much higher, in light, right? And then, in the 20th century, and then, fluorescent lamps was developed, and it gave higher, light, higher intensity light, right? And then in the 21st century, then, LEDs was developed, and then, the light is even better, right? So that gives us a basic timeline. I will give more details about this, But then, for lighting, right, again, it is also similar to what I just mentioned to you earlier, right? Those are the objectives. And then, because I'm going to jump from the regular fluorescence lamps, light bulbs, to the LEDs, I want to compare, these two different type of technologies. Oops. So the bulbs, right? The regular bulbs, right? We know that, right? The light give out, it actually it gives all directions, right? But LEDs is it give light out at the specific, more specific directions, right? So that's what we say here in terms of the directionality of the general light, okay? And also the means of evacuating generated heat is also different. So for the bulbs, it's basically through the convection. But then for the LEDs, it's more through the conduction, right? If you still have both of these light sources, and we actually, it's very easy, right? To tell the difference. And the bulbs, if we put our hands close to it, we can feel the heat, very easily. But for LEDs, it's more difficult, right? Because the LEDs is more efficient. So for the energy, the input for the LEDs, it gives out the light. But for the light bulbs, the fluorescent lamps, it gives out, other than the light, it gives out a lot of heat. So that's the main difference, right? So this is really, I want to tell you, why this is so big a deal, right? So we may not realize, okay, 19% of global electricity is actually used for lighting, okay? So, and then over 90% of that energy is wasted, right? So think about the fluorescence lamps, so that is really wasted, and also because of the directionality, right? For example, here, right? With the old lamps, okay, with the light bulbs or the fluorescent lamps, right? A lot of light actually given to the direction which we don't want them go, right? So that's why we say over 90% of that energy is wasted, right? If we can harvest that better, and we use LEDs, what we will do, we will be able to save 13.6 billion trees, right? And saving more than 1 billion barrels of oil, and saving the output of 255 power plants, right? So that's why we need to have this switch. And but everything moves in that direction, right? So this gives a little bit more details about this process, right? You see, from different times, and then it has, a different type of those lamps as well. So that's, that gives us some historical efficacy improvement of the white light sources. And then I want to look at this one a little bit more, because it really gives us, the first actually practical incandescent bulbs with a carbon filament actually were invented by Thomas Edison. Right? That was in 1879. And then 1904, the first incandescent bulbs with a tungsten filament was produced. And that really, gave the light bulbs, to more people, right? And also it lasts longer. And then in the 1932, and then the sodium lamp was first produced commercially by Philips, right? 38, and then GE invented the first practical fluorescent tube. And now you see this is related to luminescent materials now, right? And then in 1959, then GE patented the first practical halogen bulbs. And then later on, and then slowly becomes the age of the LEDs, And so the real LED was discovered by Nick Hon'ble at GE, and then that was in 1960s, right? Then organic LEDs was demonstrated in 1963, and then the metal halide lamps was introduced in 1960s as well. In the 70s, high pressure sodium lamps was produced commercially in 1970s, and then we can start to see yellow, green, and orange LEDs was produced. Okay, but this is not related to the solid state lighting we want to focus on today. Okay, and then there's the fluorescent light bulbs were first launched publicly by Philips in the 1980s. And then in the 1990s, then the blue LEDs was discovered by Shuji Nakamura at Niche, right? And he is the one received the Nobel Prize, right? Because of the development of blue LEDs. So that is, more in the 19th and the 20th century, right? So a little bit more related to this is, I want to go into this part, right? So there's later on, right, here it's 1993. So then, yeah, we got the red LEDs and then red, orange, yellow, green LEDs, right? But the brightness were also important, right? So in the 1995, high brightness blue, green LEDs was developed. So that is could really, could be commercially used, right? And then in the 2000s, then wide LED lamps demonstrate incandescent efficacy. And so that's, when we will be used for our really lighting. In the 2005, wide LED lamps demonstrated fluorescent efficacy is about 70 lumen per watt. And then in 2008, the production wide LED lamps exceed 100 lumen per watt. And then in the 2014, RGB LEDs lamp gave birth to mesobic light, which matches the sensitivity of human eyes. So that gives us, a really some history, so the current light technology, basically, right, when we look at this brief history, we can tell that the current lighting technology is about 100 years old. LEDs began as just indicators, but are now poised to become the most efficient light source ever created. Okay, for example, here actually showing some examples about solid state lighting applications today, right? Signal light, right? Our headlight of our cars, and many other things, right? Flashlight, even for police cars, right? So many of this, right? And here shows actually the difference, okay, between the fluorescent lamps and also the LEDs. We can clearly see the difference, right? And this is much brighter. So then this is the other, thing, because of the different lighting sources and even the food could become more attractive, right? You will see that, this with when we use a high quality light, this looks much attractive, right? This is with low quality light, and you will see the difference, right? And here, even with potatoes, right, you can see the difference, right? So the lighting technology is not just give us light, it has so many different, attractive aspects. And so, for us to get really the solid state lighting, right? So we have to go back to understand a little bit about what LED, how LED works, right? The LED by itself, okay, the light emit diodes. It consists of several layers of semiconductor materials, right? The light is generated in the PN junction, right? When a current applied, so you see here, right, shows the current. Then it gives out a monochromatic light, okay? And so if we really want to use it, of course, it needs to be down-converted with the phosphor. So that's what we, what we are talking more about this phosphorus, right? The color of light from the LED depends on the materials used, okay? So these are the, these layers of materials. That's important. And so there are two major material systems used to produce LEDs in all colors, right? For example, the red, orange, amber is this with this composition, and then green, blue is this composition. So it's more nitride, and this is phosphate. So so that's the key, right? In the old, before, so I talked about here, right? Here. So before this blue LEDs was discovered, it was very difficult to generate blue LEDs. And then Mura, of course, he figured out and then used nitride, and then he and his team was able to generate the blue LEDs. So that's of course, right here we are talking about the solid state lighting. We are not talking just one specific wavelength. So we are talking about white light. So the advantage of this is it contains no mercury metals, right? So this makes it more environmentally friendly, and also we use no rare or exotic materials, right? In this, nitride, phosphide, right? And also, as I showed you earlier, right? The LEDs accept a lot of more energy in use than they consume in manufacture. Okay, they are all OHS compliant, containing no substance, so very high concern, as defined in the REACH program. So, and also we can see here, in a different way to look into this when we compare to other lighting technologies, right? So this red bar shows that it's used energy. Basically, right, we need to put in energy, right? We use the electricity most of the time, right? And then they give out light. And so here we can see that, right? For the fluorescence lamps, we need to put a lot of energy in, and then it gives out the light, right? And then for the solid state lighting, and especially this one, and you can see that the used energy is much less, right? So how do we really create white light LEDs, right? So in general, okay, I just want to say in general, there are two methods, okay? So we use those LEDs and then cover it with phosphor, okay? And this phosphor, because LEDs is blue LEDs, and then it covers with yellow phosphorus, and then it will give out a white light, right? And that means the LED could be blue or the near ultra white chip, and that give us the light, and the light give out is similar to fluorescent tube or the bulbs technology. And then there's another way is use red, green, or blue LEDs, and that together also yield a white light. So that's the basically two technologies, right? But if we look into this, and you will see that, right, for those three color ones, actually it can be directly a compilation of the LEDs, right? Or we can use a LED. For example, here is near ultraviolet LED, and then it's covered with the three phosphors, right? those free phosphors is blue, green, red, and then eventually they give out the white light. And the other thing is the other design that I showed in the previous slide is with a blue LED, and then it covered with a yellow phosphor, and then that also gave out the white light. So both of these techniques got the pros and the cons, right? This one showing here, on the right side, right? On the right side is is a single LED type and easy to control, easy secondary optics and good CRI. We'll talk about CRI just in a little bit. But then the problem with this is the efficacy is not that good. Okay, and then with this design, it can give us a tunable CCD. We will talk about what the CCD as well, and the color, any color possible. Because that depends on how we make these combinations, right? But then because it's a combination, so it's more difficult to control. Then the CRI is actually low. It gives us the lowest LPW efficacy. So those are the things, among this. And then the other problem with this design is especially if we use the 3 phosphors. And those phosphors actually, and the phosphors, different phosphors actually, it will decay actually differently. And you will see, right, in this plot. And the red phosphor is relatively more stable, but the green light will decay faster. And then the blue phosphor actually, degrade even faster. And then, they combined like white light, then it's actually after certain hours, it's not as original anymore. So that's a problem with these designs. So again, as I mentioned to you earlier, right? For the solid state lighting, right? There are 3 major components. Okay, firstly is the LED chips, right? And then we will cover it with the phosphorus. And other than that, we also need to package it. So that's the 3 part. Right, of course, the LED chips determines the raw brightness and the efficacy. And then the phosphor determines the color points and the color point stability. And then packages to use to protect the chip and the phosphor. And it helps with light and heat extraction. So the packages actually has another function, okay? Helps the light and the heat extraction. It's primarily in determining LED lifetime, right? Because LED by itself is pretty stable, and so it has a long lifetime. The phosphor mostly as well, but then the package, sometimes is the wake point. That's why it says, the primary in determining LED lifetime. And this all shows, different designs, different shapes. You can see LEDs depends on the applications, right? So how do we get that, right? I'll talk a little bit about that, okay? So of course, LEDs are, nowadays is mostly efficient, commercially available white light source and improving all the time, okay? This is also very important, okay? We are still improving. That's why I'm still, spend some effort on developing phosphorus, right? Even though LED is actually technology improved a lot in the past years, okay, in the past 20, 30 years. And other than saving real dollars on energy, and then there are a couple of things, happening as well. When the LEDs becomes more brighter and more efficient, okay, then because it becomes brighter and more efficient, right? And the fewer LEDs are required for a given lighting applications, right? For example, in our room, right? we only need a certain, a certain amount of light, right? So when the LEDs becomes more efficient, then we can use fewer LEDs, right? That's really important, right? Okay, so brighter LEDs also enable penetrating higher and higher volume lighting applications. That means, the light can go further away, and so that's also important. Okay. So, and then how do we deposit phosphorus on the LED chips? So there are different ones, I'm not an expert on this, but these are the things, for us to be aware of. So these are globes, okay, and then there's a dispersed in encapsulate as well. And then, then depends on the different type of coating. This as a conformal coating, you will see that the coating is actually right on this, right? And then the chip coating or plate as well. Okay, so it's only coat on the top of the chip. So that's the thing, right? Different this type of techniques, it has their trade-offs, right? Efficacy, the CCD as well, talk about the source size as well, and the billing, the color stability, reliability, cost is also important, right? Because we are making these LEDs commercially available to everyone, right? So cost is definitely one thing we need to consider. Here I give a little bit more details about the pros and the cons of these different deposition technologies. So for those large chip and the coated phosphor systems, and then much higher drive capability and generally lower voltage, and then small source size and good for TLR optics, and then the looming 80, and so it can get the looming 80, so it's energy store, right? But then the cons is the CCD, uniformity of light, and then because they are large chips, right? So that's makes it more difficult. And then when there's a small chips, and it is with the dispersed phosphorus, and then the CCD is good, the uniformity is also high, and then get the looming 80, but then the drive capability is low, and also a large source size for secondary optics, because it's coded like this way. And then this one is really like the FlightX. That's why it's called the FlightX. And tons of light, thousands of lumens. Okay, easy to use, but the efficacy is low. Thermal and billing challenges. So those type of things, right? Huge optical source. So those are the problems with that. And then, once we have the LED, LED lighting systems, white light LEDs, right? So how do we categorize it? Okay, so far I haven't really talked about it, right? Even though I used a couple of terms so far. So this is really important. Okay, because for electricity, right, we use volts, and then we use amps, right? We use, but for light, how do we do that? Okay, so because light is related to the wavelengths as well, right? So it's more challenged technically. So for example, right, for our warm light, like for our indoor light, we prefer to have warm white light, right, which is similar to the solar light, right? And so we just say warm white light, right? But other than that, we don't know much details about it, right? It's descriptive, okay? So we do need more specific characterization techniques for that. So there are different ways, in the literature, actually, when we talk about, a white light, and actually, the one is using this spectral power distribution, right? Basically, just like the the spectrum, spectrums, and also, there's chromaticity diagrams, something like this. And because this is a diagram like this, so we normally use coordinates, right? Depends on where it's located, right? And then there's a color temperature as well. Color temperature normally is only one number, but for chromaticity, and it's 2-3 numbers. So to do this, right, to describing color, and is actually very important thing for us to understand is actually related to us, to our eyes, to our vision. It's not just related to the phosphorus or the lighting source themselves. Okay, so that's why I want to bring this up a little bit, to understand, how human eyes works, and understand how light works as well. Okay, so if we look into this, right, the functioning of the eye is different for outdoor way versus indoor, right? And also depends on whether it's light time or the daytime, right? So you see here, this is a starless light, so which means it's pretty dark, right? Full moon light, okay, and then indoor lighting, and then sunny days, photo flash, and you will see that, especially this part, and then for example, the retina luminescence, and then active for photoreceptors and the vision mode, and we will see that it's actually quite different. So, for example, the active photoreceptors at nighttime is actually with the rods, and then for the daytime is with the cones, right? That's our receptors in our eyes, right? So if we look at the anatomy, and then we will know that all eyes work the same around the world. Okay, doesn't matter from people from which continent, from which origin. Okay, that's for sure. But then the thing is, the cones are for colors and daylight. Okay, which is about 5 million, and then the rods are for motion and light vision. Okay, so there are more rods in our retina for those functions. And then also, we know that, right? We know our humans, our vision will change with our age, right? It's because of the cones and the rods, are changing as well with our age. So in that way, our perception by different people is actually different. Okay, so while the phosphor may, the light source may emit the same amount of light, but different people will view it differently. How to characterize that, right? That's really the key, right? That's what we are talking right now. Okay, so yeah, I think I need to speed up. I try to get as much details as possible. But anyway, so if we look at these two spectrums, right, and then also, keep in mind this is a sunlight spectrum, right? And we will see, the question here is which one is closer to the sun, right? So that's something, always something, when we have different phosphorus, different light sources, we need to consider. Okay. Then this is a CCT, is actually the full name is related color temperature. And that's what we say, there's only one number, right? So this is the temperature. So we normally use a K. Normally we want to get warm light, then this number should be larger. And then, again, this is what I say, people's ability to discern differences in the color varies by CCT, okay? So in general, okay, we should specify our LEDs and design our systems tightly for indoor and warm colors. But for outdoor and the cooler CCTs, that should be more loose. And we can do that, design LEDs more loosely. And then the other term, the other parameter widely used is color rendering index, CRI. And this is actually first proposed in the 1950s. And again, as I showed you, these are characterized by the coordinated coordinates. And and then the other thing is in color center bulbs was actually by definition has a CRI 100. And so then the other light source is based on this. And so that's what we see here, right? The color center lamps has a CRI 100, and then for the other type of LEDs, mostly LEDs, fluorescent lamps, then we can see that CRIs are different, okay? And then, depends on the color rendering and the color quality in our real life, we can see that even though these two are the same, but when the CRI or CRI values are different, and then we can see, they have different colors, and also, one is more appealing than the other, right? Even for our fruits and vegetables, so that's why a light source with a high CRI is so important. And then there's another parameter people use is the McAdam eclipses, and so it's similar to the CRI diagram. But people use this eclipse to demonstrate that, and depends on how big this eclipse the size. And so then the other thing is, if we make a lot of LED light sources, right? How do we make sure this one is the same as the other one, okay? Or they are similar, right? So that is use a new term. It's called billing. This is the root cause. Because our human eyes are extraordinarily sensitive, so small process variation in the LED chip wavelengths, and then also phosphor thickness and concentration, composition, and the deposition condition make a big perceived difference in white light CCT and the quality. Okay, so that's in commercial in industry, the billing is very important. So to make sure the lamps we purchase are similar, then it's covered by the billing. So for the solid state lighting, is actually one important thing I want to emphasize here is a multidisciplinary effort, right? So far, you see, I spent a lot of time talking about the optical aspects only, right? But remember, there's a thermal process, electrical process as well. So then we will be able to deliver specific lumens, and so that's why this is multidisciplinary effort. So this is related to that. So the thermal part is the source of lumen depreciation. So we want to make sure all the components have a good thermal stability. So there's slow or little lumen depreciation. The optics related to the lenses is also very important. The driver, right? Basically, the drive, right, by the electricity, right? So the electrical losses in power conversion should be low. So that's the thing. One important thing about this is, we get back to why this LED could be a big deal. It's, remember, right, for our transistors related to our computers, laptops now, right, you start with vacuum tubes, right? And then, for our information storage, right, old times, some of us maybe remember, right, we use VHS, but now we use the DVDs, and then, and then later on people use the DVDs. I mean, nowadays actually, most people don't use the DVD anymore, right? And then for the TVs as well, right, for the film, and now we use a flash memory, and all the time we use the brick phones, and now people use the smartphones, right? So that's the same thing happens to the LEDs, right? Just as I showed here. Then the other thing is we all know that the Moore's law, right, for transistor cost. Okay, so it shows this. LED is actually even goes much faster than the transistors. And so to develop a new phosphors, right, there are different designs. So that's what I want to go back to this as well. I showed you a little bit before, but in academia, in research side, they are different still, have different type of designs. So these two showed with the blue chips, okay, blue LED chips, right? And then, one way is with the yellow phosphor. If we can develop really a good yellow phosphor, that will be good. And then blue chips can combine with red and the green phosphors, and also it gives out white light. And then if we use near UV LEDs, there are two designs as well. So this uses RGB phosphors, and then this is use white phosphors. If we can design a white phosphor, and then we just need one phosphor, we put on the near UV chips, right? So you can see this. We didn't talk about this type of phosphor before, right? But white phosphors nowadays actually it also has been explored. Okay. Then this one RGB phosphors, it can be 3 phosphors, right? Or it can be 2 or just 1 phosphor, as long as it gives this red light, red emission, green emission, and the blue emission. Okay, so those are the details I want to point it out. Of course, in that way, this RG phosphor could be 2 phosphors or just 1 phosphor, right? So how do we develop, design this type of phosphors? So these are the different strategies, scientists have been explored. And so we use these different strategies to control the luminescence of phosphors to match the LED applications. Okay. So far, I've been talking about the LED applications for our lighting, right? But for our indoor or outdoor lighting, but also LED has been used for forming as well. Okay, because our plants actually can grow faster at different excitation wavelengths. So so that's the other aspect. Okay, so how do we control the luminescence of phosphors, right? So there are 4 strategies, and then here, the first one is select a crystal structure. Basically, this is called the crystal phase engineering, right? And then the other one is modification of composition, right? That is crystal field effect. And then the third one is coupling to host lattice. It's crystal site engineering as well. And then the last one is the design of energy transfer, because we add activators, right, in the phosphorus. So those activators cannot be just one, right? It can be multiple. So if we use multiple, and then we can tune the ion and ion interactions within the host materials. So those are the different strategies. And so earlier I talked about in the last couple of days, I talked about this type of nanoparticles we've been working with, right? I don't want to go to the details, but if you are interested, you can go back. But today, the phosphor I'm showing is based on this composition. Okay, this is how the synthesis process. This is a little bit background about this type of compounds. I'll skip this, and so get back to the material we've been looking at. It's actually it's doped lanthanum half-lit nanoparticles, and here we doped them with 3 different type of dopants. So here we can see that with the different dopants, actually we can different colors, right? This one is doped with the europium, and then you can see this one gave out green light, and so we can see that, right? So this is the terbium gave out the green light, and this one, dysmanium, is given more, light in this region, right? And the europium gives the red light. So we've been thinking about, so if we put these 3 together, right, it's close to give us white light. So especially if we can tune the composition of this, doping levels of these three dopants, right? They could get white light and warm white light. So that's our goal. And then we did that. Okay. So we doped, it's called a triply doped sample. And then we also tuned the concentration of these three, right? And then, and then we can see that, we get the light, we get the CIE index, at different, different coordinates. And then the CCT also could be tuned. So that's one example, we can see that. So this is one host material, but with three dopants, right? So with this design, it should have better, stability, right? So it's something similar to this one, right? So to this design. So that's what we are trying to talk about. So with that, it's also almost time as well. I want to end here with acknowledge my research group and also the funding and the collaborators. So if you have any questions and comments, please go ahead.
Dr. Fan.
Hello, Professor Mao. We are back with the questions. So
Great.
I would like to share with you the first question. It is, how much heat release compared to older technologies do we have in such materials?
Oh,
Can
okay.
it cause global warming?
Yeah, that's related. Yes. So exactly as I'm showing here, I don't have specific numbers, but the heat is a big difference. One thing I always, when people ask me this question, is like, just get the two light sources, and then we get our hands close to them. We can feel the difference.
Do light from LED bulbs that we use nowadays produce health hazards in humans?
No hazard elements. That's the other advantage of this. Yeah.
Okay, so in doped nanoparticles, like lanthanide doped nanoparticles, on one side we have enhanced photostability with large Stokes shift. Is it enhanced photostability to do with structural reorganization, or is it a consequence of band gap changing?
That's a question. So, yes. So this host material, right? It should have a large band gap. So that's why we selected the lanthanide hafenate. And yeah. So in terms of the wavelength conversion, and again, as I mentioned earlier, there's always there would be always heat generated. So, but with this combination, it gives us very good white light, warm white light.
Why is the transfer of electrons from excited to metastable state non-radiative?
Oh, I think one thing is I don't think I said that, and they will be in most of the time they will be non-radiative process always. The most important thing for us to design phosphorus is to minimize that. Yeah, there will be, and from our samples, for example, like this lanthanide hafenate, doped lanthanide hafenate nanoparticles, we always see these non-radiative processes. Yeah, they will be. They will be. I mean, if we can get the systems like that, that would be amazing.
Could you please comment on the suitability and future of carbon dots or graphene quantum dots in solid state lighting?
Yeah, that's I know there's that's a hot topic recently. Yeah, I think that's going to be very promising. You know, I know that, for example, the quantum efficiency has been improved a lot in the last years. I think that should be an area, you know, we should explore. And it could have a great future as well.
Can we say white light is monochromatic?
Oh no, right? White light is not, right? Because it covers the visible range. That gives us white light.
Then could you please highlight the pros and cons of using white LEDs over mercury or xenon lamp in various applications such as hydrogen generation?
Hydrogen generation, okay. I mean, obviously, right? Because LEDs are more efficient, right? But by the lighting process is already more efficient, right? So overall, you know, when we combine it for example, like water splitting, and that will improve the overall efficiency, right? So definitely, you know, LED could be preferred.
What could be the greener perspective of designing phosphors without harming the environment?
The greener process?
Yes, green methods.
Green methods, okay. I mean, for the green chemistry, right? There are 11 principles, right? Each of those could be considered. I mean, from the source material, from the synthesis process, you know, from the amount of generated waste materials, you know, we all can consider, right? Of course, right now, for example, right, you know, one direction is try to develop rare earth-free doped phosphorus, right? Because in general, rare earth elements are quite difficult to get. I mean, get pure rare earth elements, and then we can use them, right? And the cost is pretty high. And if we can get away from rare earth dopants, and that would be wonderful. I mean, in the past 10, 20 years, there are quite some studies on this aspect, but nothing is close to commercialization. So
yeah, we hope to see a better future now.
Yep. Oh, yeah. That's why we do science, right?
Yeah, I think we are over with the questions, and it was a marvelous presentation about designing phosphors. The commercial perspective was so much highlighted, and there was so much elaborate data. Discussion was so intriguing from the future prospects of designing phosphors. You've been keeping our enthusiasm very high, Professor, by touching interesting topics and specifically highlighting the commercialization bottlenecks and the perspectives as well. The diversity of your discussions are truly amazing, and they are adding new dimensions to the knowledge pool of advanced functional materials. We are eagerly waiting to hear your lecture on exploration of wavelength conversion nanomaterials. We would request you to, if you can, you know, possibly share the links of your published papers so that the participants, you know, later on can go through your remarkable research work. We are very thankful for you for being with us. It was a great day today, like always, and we are looking forward to hear from you tomorrow. Have a great day, Professor Mao.
Thank you very much. Thank you very much. Looking forward to speak tomorrow again. Thank you.